Hi guys, Rod here. This is an introduction to assembly language programming in general as applied to the Atmel ATmega644A used at Dalhousie. This is mostly for those taking ECED3204 microprocessors. In talking to many of my classmates, I came to realize that many of them were lacking a foundational understanding about microprocessors and microcontrollers that you really need to start programming in assembly language or ASM. So I thought I'd see if I could help. In this video, we will cover what is a microcontroller. Next, how does a microcontroller actually do something? Within that topic, we will cover memory, which is data, program, and counters, instruction set basics, registers, what are they? This will also include flags. Then we will move to ASM, what it is and how does it relate to the instruction set, and the anatomy of an ASM program. And lastly, we will look at your first ASM program. Part 1. What is a microcontroller? Computers are electronic devices that basically consist of three major components: a central processing unit, or CPU, a data storage method, which is memory or hard drives, and input and output circuitry, keyboard, mouse, sensors, screens, speakers, LEDs, etc. A microcontroller basically puts those components into a single package. Microcontrollers are different from larger computers or the system on a chip in your cell phone only because of their scale. They have lower processing capabilities, smaller amounts of memory, and much simpler I/O circuitry, but that also makes them comparatively inexpensive. Having all of these components integrated into a single package also makes them easier to use because you neither have to deal with building the support circuitry to interface memory to CPU to inputs and outputs, nor do you have to deal with the complex packages used for SoCs such as this. Part 2. How does a microcontroller do something? Microcontrollers are not just collections of empty ports. They have been designed and built with certain functions already in them. One function is to copy the contents of one memory location to another location. The collection of these built-in functions is known as the instruction set. All Atmel AVR microcontrollers use the same basic instruction set. The instruction set is referred to in the microcontroller by a binary number that is 16 bits long. While this sounds like there could be thousands of instructions, in reality, most of the instructions are encoded by the highest 6 bits, and the rest of the binary code deals with variations of the instruction for different registers and such. We will deal with registers shortly. This microcontroller keeps a list of the instructions you want it to do, the program, in part of its memory. Now, we often think about memory as little slots, but in reality it is just a large collection of bits that are accessed with access lines. Humans divide that collection of bits into bytes of 8 bits. It is easier for us to handle them if we think about them that way. Each byte of memory needs to have an address so we can refer to it specifically. If we only used a single byte to refer to memory locations, we could only have 2 to the power of 8 memory locations, or 256 bytes. This is actually what computers used to have, but it's far too small for what we want to do. If we use 2 bytes, we have 2 to the power of 16 memory locations, or 65,536 locations. This is 64 kilobytes of storage, and we can divide that up into 256 rows and 256 columns of data, if it helps you think about it. The ATmega644A has 64 kilobytes of flash memory, 2 kilobytes of electrically erasable programmable read-only memory, or EEPROM, where it keeps its bootloader and certain system programs, and it also has 4 kilobytes of SRAM, which is where it keeps temporary data, such as registers, that is lost when the power is removed. All of the activities of the microcontroller take place in the SRAM portion of memory. The microcontroller keeps a program counter here that points to the next instruction in your program that it should do. So every time the microcontroller gets an instruction from your program, it increments the program counter by the length of your instruction so that when it comes back, it knows where to get the next instruction from. This is because the microcontroller is like a one-armed robot. It can only work on one thing at a time, and it can only hold one thing at a time. In order for it to remember something from your instruction, it has to put down the program counter and pick up your instruction. Important. This means that each instruction is self-contained and does not refer to any other instruction. I'll say that again. Important. Each instruction is self-contained and does not refer to any other instruction. So, how is it that programs string commands together to accomplish anything? How can you do it? The microcontroller has a part of its memory set aside to store temporary data called registers. Registers are just like memory locations, like any other memory location in SRAM, except that the instruction set refers directly to those memory locations. There are several different types of registers. There are 8-bit registers, pairs of 8-bit registers that are meant to be used to hold 16-bit values, but you can use them as separate 8-bit registers. And there are certain registers where each bit has a defined meaning. And there is a collection of registers set aside to be used as a stack. From our perspective, the more important registers are the input-output registers. When set up properly, bits set in an output register appear at the physical pins of the microcontroller as highs or lows. And highs or lows placed on the physical pins of the microcontroller appear as a set or unset bits in the input registers. This is how your input and output is communicated outside of the imaginary world inside the microprocessor. Part 3. ASM. What is it and how does it relate to the instruction set? As I previously mentioned, the microprocessor has all of its instructions set stored in memory and accessed by 16-bit opcodes. Humans have a hard time remembering long numbers, especially 16-bit binary numbers. ASM is a low-level language that represents the opcodes as short words or acronyms. For instance, the opcode 11100000000000 would be hard for you to remember, but the ASM line, LDI, R0, 0x00, is much easier to understand. Yes, those two things mean exactly the same thing to the microcontroller. So the ASM commands, such as LDI, are just English-type versions of the opcodes built into the microprocessor. The same important note remains, however. Each ASM command is performed in isolation. The microcontroller doesn't remember anything from one command to the next. There are other portions of ASM that are not opcodes. There are assembler directives that tell the assembler how to handle the code, or that make it easier for you to understand your code or change it later. Each ASM line is composed of an optional label, a directive or an instruction, a possibly optional argument or operand, and an optional comment. An example of an instruction without anything else is the NOP instruction. An example of an instruction with a label and operands is loop, CP, R0, R1. This compares register 0 to register 1. The label is used by the assembler to refer to the memory location that contains the CP directive of your code, so they can replace it with an actual address if you want to jump back to it. That way you don't have to know how many bytes your code is and where the CP is, and you don't have to change the address if you modify the code. The assembler does all that work for you. It is actually possible for you to look up all the opcodes and assemble your code by hand, but that is more work than you need to do. Part 4. The anatomy of an ASM program. An ASM program is run in order. The first instruction is executed first, then the second, etc., unless there are codes that cause the program to jump to another section. When the assembler is working on your code, it knows this and expects things to be defined before you use them. For this reason, the very first part of your code is the include directive that includes all the information the assembler needs to build your program for your specific microcontroller. For our microcontroller, the line is include M644A-DAF.inc. Next is the instruction of where to start the program in memory. This is also an assembler directive. Think of it as origin.org $0000. Lastly, there are two lines. JMP start is the directive to jump to the place labeled as start, and then there is the line labeled start. The instruction at start is up to you. If you want your code to loop indefinitely, then your last instruction in your program will be rjump start, or relative jump back to the start. Part 5. First ASM program. The first ASM program in the course is the blinkasm.s program in Lab 01 shown here. You should be able to load this program into your Atmel Studio, compile it, and upload it to your board. Let's take a look at the first couple lines and see what they tell us. Here we have the standard include for our microcontroller. Next is an assembler directive to define the word temp as referring to register 16. That way, if we want to change to register 17 or another register, we only have to change it in one place, and it will be changed by the assembler throughout our program. When the assembler is assembling, on its first pass, it will change every instance of temp to R16 or R17 or whatever we have there. Next is an assembler directive equating delay constant with the value 1 million. The assembler will replace this as well. Lastly is the origin statement to start the program at $0000 or the bottom of memory. So the next section jumps to the reset section, which is the initialization section of the code. Here we see some values that we didn't plug in ourselves. RAM-end and SPH/SPL are both provided by the include file. The size of the memory, which is RAM-end, and the location of the stack, SP-high and SPL-low, are different depending on the microcontroller you have. These instructions push the value of RAM-end onto the stack pointer, which basically deletes the entire stack. DDRB is likewise an address pointed to by the include file. This out directive sets bit 0 of the data direction register for port B to 1 and the other 7 to 0. This means pin B0 is now an output. This is the main loop of the program. It starts with a label of main, so that we can jump here from many places. It is only an assembler directive. SBI is the instruction or opcode to set a bit with the immediate location. In this case, it sets bit 0 of port B, and set makes it 1. Then it does a relative call to the section of code starting at the label DLY. This code executes, and when it hits an RET or return, it comes back here. CBI is the opposite instruction to SBI. It clears bit 0 of port B, or sets it to 0. Then there is a delay again, and then the program jumps, or relative jumps, back to main, which means it loops indefinitely. This is the delay function. It loads registers 17 through 19 with the delay values we set originally. Then comes the interesting portion. The first instruction is a SUBI. This subtracts 1 from the contents in register 17. If register 17 is ever all zeros, then we need to borrow 1 from somewhere. This is the carry bit being used as a borrow bit. The next two instructions are SBCI, which means to subtract 0 from each register, but it also accounts for the carry bit, which is also subtracted. Because we are dealing with binary, it just continues the subtraction as expected. Second last is a branch if carry cleared. The carry is cleared each time the SBCI has more numbers to work with that can account for the carry. This means that as long as R18 and R19 have value, the loop will continue and the BRCC sends the microcontroller to the program counter -3, which is back to the sub-I R17-1 instruction. If the carry is not clear, the program continues past the BRCC to the RET and the delay is done. Part 6. So there you have a basic overview of how the microcontroller works and how it thinks. Join me next time when we will go over the answers to the first assignment so that we can work through them. Cheers!